Hi students, good morning. In the previous session, I have discussed about the nodes, that is in that nodes what are the radial nodes and angular nodes, how to calculate the radial nodes as well as the angular nodes, and also I have discussed about the quantum numbers, that is different types, that is 4 types of quantum numbers: principal quantum number, azimuthal quantum number, and magnetic quantum number, and spin quantum number. And also I have discussed about the different shapes of the orbitals, that is s orbital, p and d orbitals. In this class we will start the filling of electrons in the atomic orbitals. What are the rules that are there for the filling of electrons in the orbitals or subshells? Coming for the filling of electrons. Filling of electrons in an orbital. Here the filling of electrons takes in an orbital according to Hofbauer's principle and Hund's rule of maximum multiplicity, Pauli's exclusion principle, as well as n plus L rule. Based on these, we are going to fill the electrons in an orbital. First one is Hofbauer's principle. In Hofbauer's principle, here Hofbauer means not the name of a scientist, okay? It's it's the word that is derived from German. It is a German word which means construction. In Hofbauer's principle, here this explains how to fill the electrons. That is, first it tells about the energy in an orbital or subshells. How the energy is in the orbitals or subshells. Also it tells about the electrons, filling of electrons in an orbital or a subshell. It tells about the filling of electrons in a orbital or subshells. This is the main thing that you learn in Hofbauer's principle, that is energy. Here according to Hofbauer, what it says means the filling of electrons takes place in the increasing order of the energy levels in the subshells. That is the Hofbauer's principle. Here I will explain you all how to fill the electrons according to the increasing order in their energy level. See here, for the construction of the Hofbauer's principle, if this is 1s, 2s, 3s, 1s, 2s, 3s, 4s, 5s, 6s, 7s, then 2p, 3p, 4p, 5p, 6p. Next comes 3d, 4d, 5d and 6d. Next is 4f and 5f. Here coming for the filling of the orbitals, electrons filling in an orbital. First the electrons fills in 1s subshell, then in 2s, then 2p 3s, then 3p 4s, then in 3d 4p 5s, then 4d 5p 6s, then comes 4f 5d, then 6p 7s. Like this the filling takes place in the increasing order of the energy levels. Let us see how it takes the filling here. First is 1s. 1s is filled. Next is what? 2s. Then 2p. Then is 3s. Then comes the, after this 2s, 2p, then 3s, then 3p. The filling of 3p takes place, then comes the 4s. After 4s, 3d, then 4p, 5s, then 4D, 5P, 6S, like this it goes on. After that 4F, 5D, 6P, 7S. Like this the filling of electrons takes place in an orbital, in the subshells of an orbital. This is the of-Boss principle, that is filling of electrons takes place in the increasing order of their, in the increasing order of their energies. Energy, depending on the increasing order of the energy, the orbitals is filled, the electrons is filled in an orbital. That is nothing but of-Boss principle. In this only the filling of these takes place in the increasing order. How? By taking the n plus L rule. According to n plus L rule, the filling takes place here. The energy here, as I said, the filling of electrons takes place in the increasing order of their energies. This energy is directly proportional to n plus L value. If the orbitals or the subshells which are in the orbitals, these subshells have the same n plus L value. If they are having the same n plus L value, then what happens, which has the least n value, that is filled first, then the value which has highest n value is filled afterwards. Then if the n plus L value is less compared to the other subshell, what happens, the filling takes place in the one which has the less n plus L value first and then the highest. I will explain how it is now. If there are, according to n plus L rule, if I take the example of 4D and 5S, you all know that these are the subshell, D and S subshells, 4D and 5S here. This n means what? Principal quantum number. Here n means principal quantum number, L means azimuthal quantum number. If here the value of L for SPDF, I have explained in the previous session that the values for L for S is 0, for P is 1, for D is 2 and for F is 3. This is the value, that is for S0, P1, D2 and F3. This is the azimuthal quantum number value for these subshells. If I apply this rule, n plus L rule for this subshell, that is 4D subshell, what happens? N value is what? N value is here is 4. Then D, the value of D is 2. 4 plus 2 is what? 6. You get 6 here, the value as 6. For 5S subshell, n plus L value is, n value is 5 and L value is, S is 0. Here the value is 5. 5 plus 0 is 5. Now, how you will fill here? How the filling takes place in this? You all can see the value for 5S is 5 and for value for 4D subshell is 6. As I said, according to n plus L rule, the one which has the less n plus L value, that is filled first in the electronic configuration. The one which has less n plus L value is filled first. It is filled first. Okay. The one which has the less n plus value is filled first, means first which fills here, 5S subshell fills, then the filling of 4D subshell takes place. Here you all can see here, first which fills here, 5S fills, then the 4D subshell is filling here. If they are having the energy of n plus L value is less, then that is filled first, then the highest n plus L value is filled. If n plus L value is same, if it is having same energy, that is n plus L value. What happens? If I take 5D and 4F. I will take 5D and 4F here. This subshell. Here n plus L value for 5D is what? 5. D value is what here? 2. 5 plus 2 is 7 here. For 4F, n plus L value is 4 plus F value is here 3. 4 plus 3 is 7. Here you all should observe that n plus L value is same for both. They are having the same n plus L values. That is 4D and 5F is having same n plus L value. If they are having the same n plus L value, what we should do? We should see the n which is having the highest or the least n, you all should see first. Here I am saying which is having the least n. Here 4F is having the lesser n value. That is principal quantum value is n is less here. It is having 4 here. N is equal to 4 means the filling takes place first in the least n value, which is having a less n value is filled first, then the filling takes place in 5D. Here if n plus L value is same, then what we should do? We should see which is having lesser n value. That should be filled first. So here which is having the less n value, 4F is having the less n value. 4F is filled first, then filling of 5D takes place. Here you all can see here after this 7S, here 4D, 5P, 6S, then 4F, then 5D. The filling of 4F takes place and then the 5D subshells fills here. This is the of-pause principle based on n plus L rule. Depending on the n plus L rule, we will classify and we give a filling of electrons in an subshell of the orbitals. There is an exception case of off-pause principle, that is in hydrogen atom as well as helium, He plus ion as well as lithium, Li2 plus ion. That is, they are single electron species. I have explained in Bohr postulate about the single electron species, that is H plus ion, that is hydrogen, helium, He plus and Li2 plus, where helium, lithium and hydrogen, they are having a single electron species. We cannot apply this n plus L rule for this single electron species. Here in this single electron species, exception case in off-pause principle. That is, as I said, the hydrogen and helium and lithium. These three are having what? These three are single electron species. These are single electron species. For this single electron species, we cannot apply n plus L rule because there is no n value for this, because they are having each are having single electrons in it. That is, if I take 1s, 2s and 2p subshell. Here the energy always is proportional to n, principal quantum number, not the azimuthal quantum number. If I take 1s, 2s and 2p, it only, I can say that this is lesser compared to this, but there is no difference between 2s and 2p here. They both are having the equal energies according to hydrogen, helium and lithium ions. They are single electron species. This is one of the exception in the off-pause principle. Coming for the second one, that is Pauli's exclusion principle. Pauli's exclusion principle. In Pauli's exclusion principle, here according to this principle, what they say means the filling of electrons or no two electrons in an atom can have a same set of 4 quantum numbers. No two electrons in an atom can have same set of 4 quantum numbers. This here according to Pauli's exclusion principle, it tells that no two electrons in an atom can have a same set of 4 quantum numbers. You all know that there are 4 quantum numbers, that is N, L, M and S. There are 4 quantum numbers, and in one subshell maximum how many in one orbit I can occupy only 2 electrons. Maximum 2 electrons can be occupied in this subshell or orbit. Here if the N value is 1, L value is 0, M value is 0. Then spin is plus half or minus half. Maximum 2 electrons it can occupy, that too in opposite spin. If it is having a quantum number N, L, M, that is 1, 0, 0, that is plus half. If it is having 1, 0, 0, it is minus half. Maximum 2 electrons can be occupied in this, not the 3 electrons cannot be occupied in this orbital. According to Pauli's exclusion principle, what it says means in a subshell or a orbital, maximum two electrons can occupy its place, and they should be of opposite spin, and they should be opposite in spin. This is the Pauli's exclusion principle. As I said, in a orbit, maximum how many electrons it can occupy? 2 electrons. That too opposite, one is this like this clockwise, the other one is anti-clockwise. This is Pauli's exclusion principle. Here according to Hund's rule of maximum multiplicity. Here what this Hund's rule says that according to Hund's rule, in a subshell of an orbital, there are different subshell in an orbital. If I take S orbital, it is spherical in shape, there is only one orbital. If I take P subshell, how many degenerate orbitals are there? There are 3 degenerate orbitals in the P subshell, that is Px, Py and Pz. And in D subshell, how many degenerate orbitals are there? There are 5 degenerate orbitals, that is dxy, dyz, dzx and dx square minus y square, then dz square. There are 5 degenerate orbitals in this D subshell. Here according to Hund's rule, what it says means the filling of degenerate orbitals should take place singly first, then the pairing takes place. If I take here 2px, if I take the filling of electrons here in px, py and pz. If px is filled first, then filling takes place in py, then takes place in pz. But before filling, there should not be pairing taking place. That is the rule of Hund's. Then only after each subshells or the degenerate orbitals are singly filled, then only there is complete that is pairing of these subshells taking place. This is the Hund's rule. That is, each degenerate orbitals or you can tell as subshells are singly filled. They are singly filled first. They should be singly filled first. Then only pairing should take place. Pairing should take place. That is the Hund's rule of maximum multiplicity. Each degenerate orbitals or subshells. Here I am taking Px, Py and Pz. Each are singly filled first. Then the pairing should be taking place. Then only the pairing should take place. This is the Hund's rule of maximum multiplicity. So, you all came to know how to fill the electrons in an orbitals according to Hofbauer's principle and Pauli's exclusion principle, and also the Hund's rule of maximum multiplicity. Now, let us come for the filling of the electronic configuration up to elements, 30 elements, that is Z is equal to 30, atomic number which are having up to 30 elements. Electronic configuration of elements up to 30 elements which are having atomic number up to 30 elements. Filling of the electronic configuration of elements up to 30. Why I am taking 30 elements means there are inside these 30 elements there is some exceptional cases of some elements here. Will come what are the exceptional elements, which are those, we will come to know how the filling takes place in these exceptional elements. Coming for hydrogen, the atomic number is what? 1. At 1 is the atomic number for hydrogen. And how to fill the electronic configuration? Filling of electronic configuration, you all know that 1s1. This is the electronic configuration for hydrogen. 2, atomic number 2 means helium. Filling is 1s2. Atomic number 3 is hydrogen, helium, lithium, then comes beryllium, then boron, then carbon, nitrogen, oxygen, fluorine and neon. These are the 10 elements which are having the 10 atomic numbers. If I come for lithium, it is 1s2, 2s1, that is total is 3. For beryllium, 1s2, 2s2, then 1s2, 2s2, 2p1, because 5 after 2s 2p comes. For carbon, 1s2, 2s2, 2p2. Then for nitrogen, 1s2, 2s2, 2p3. For oxygen, 1s2, 2s2, 2p4. In S subshell, maximum 2 electrons it can occupy. In P subshell, maximum how many electrons? It is 6 electrons, because how many subshells are there, degenerate orbitals are there in this orbital? There are having 3 degenerate orbitals in the P subshell. Therefore, maximum I can fill 6 electrons in this P subshells. And in D maximum there are 5 degenerate orbitals. So, here maximum I can fill 10 electrons. In F subshell they are having 7 degenerate orbitals, maximum I can fill 14 electrons. Next is fluorine, 1s2, 2s2, 2p5. Coming for neon, 1s2, 2s2, 2p6. This is the filling for 10 electronic configuration, how to fill for this 10 elements, first 10 elements. You all came to know how to fill the electronic configuration for first 10 elements. You all know that this P subshell is completely filled in this neon, therefore it is a noble gas or inert gas we say. Coming for the atomic number 11, that is sodium, 12 is magnesium, 13 is aluminum, 14 is silicon, 15 is phosphorus, then 16 is sulfur, 17 is chlorine, 18 is argon and 19 is potassium, 20 is calcium. How to fill the electronic configuration here? You all know that after after neon, that is 1s2, 2s2, 2p6. It comes 3s1. Then magnesium 3s2. Aluminium, neon 3s2, 3p1. Then for silicon 3s2, 3p2. Phosphorus 3s2, 3p3. Then 3s2, 3p4. For chlorine 3s2, 3p5. Then 3s2, 3p6. Then for neon, for this potassium 3s2, 3p6 and next comes what? 4s1. Then for calcium it is 3s2, 3p6, 4s2. After 21 is what? Scandium, titanium, vanadium, chromium, manganese, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. That is 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Up to 30 I have written here. For this scandium, how you will write after this? Argon, I can take argon, it is completely filled up to 3p6. Argon, then comes what? 4s2, that is 20 it is. Next is after 4s 3d1, it is 3d1. For this titanium argon 4s2 3d2. Then for vanadium 4s2 3d3. For chromium argon 4s2 3d4. No, we can't represent it as 3d4. It should be 3d5. This is the exception case in the filling of electronic configuration in the orbitals. It does not obey the off-pause rule here. This chromium also, I will explain why. And then manganese, argon, 4s2, 3d5, that is 3d5. Then for iron, total is 25, that is 18, 20, 25, 4s2, 3d6. Then comes argon, 4s2, 3d7. Nickel, argon, 4s2, 3d8. For copper, argon, 4s2, 3d9. Is it 3d9? No. Even this is the exceptional case. It is 3d10 here. Then comes for zinc, argon, 4s2, 3d10. This is also an exceptional case. There are two exceptional elements in the filling of electrons which does not obey the off-pause principle, that is chromium as well as the copper. Here this chromium and copper, when I take this chromium and copper, here this D subshell is half filled, it is half filled. And here the D subshell is completely filled. We say that the half filled as well as the completely filled subshells, they are having the more stability. They are more stable. I will explain why the half filled and the completely filled subshells are more stable by taking an example of chromium also. I will explain here now how the completely filled as well as the half filled subshells are more stable. Coming for that, why half filled and completely filled subshells or degenerate orbitals. Degenerate orbitals are more stable. Why this degenerate orbitals which are having a half filled or completely filled subshells are more stable? We will come to know about this. For this explanation, I need to know about the exchange energy and pairing energy, also promotional energy. You will know about these three things. How the exchange, what do you know about, you'll know about what is exchange energy, pairing energy and promotional energies in the completely filled as well as a half filled subshells. Here, before knowing that, we will see how it is more stable. First, coming for symmetrical charge distribution. Symmetrical charge distribution. Symmetrical charge distribution means what? You are going to distribute the electrons equally in the subshells. If I take P subshell, how many degenerate orbitals are there? There are having 3 degenerate orbitals. In this P subshell, that is Px, Py and Pz subshells. If I want to say it is symmetrical means what? Each should have 1 electron. If I have a 300 rupees, okay, I am having a 300 rupees. I am giving that 300 rupees for this one student only means, is this a symmetrical distribution? No, it is not a symmetrical distribution. If I am going to divide it equally between these 3 members, that is 100, 100, 100, then we say it is a symmetrical distribution. So here, if it is having a single electrons in each, then it is half filled. We say it is half filled. Also, if this Px, Py and Pz subshells are having fully filled, completely filled or fully filled, means there is a symmetrical distribution of charge taking place here. There is a symmetrical distribution of charges taking place, or the symmetrical distribution of electron is taking place in this subshells. Then they are stable. It is half filled or completely filled. It is stable. We say it is stable. Next is exchange energy. You will know about what is exchange energy. We will come to know about exchange energy. I am taking D subshells here. How many subshells are there in D? There are 5 degenerate orbitals. That is 1, 2, 3, 4, 5. They are having equal energies. You all should know that they are having the equal energies. Here I have explained you all that for P subshell, what will have half filled means 3 electrons, completely filled means 6 electrons. In D subshell what happens? It is having a 5 degenerate orbital, so 5 electrons should be there for half filled, and for completely filled there should be a 10 electrons. For F subshell 7 and 14. But for S, it is an exceptional case. In S subshell you all know that there is no orientation, there is no particular axis for S subshell, and it is spherical in shape, and there is a probability of finding an electron is equal. Therefore, exceptional case is S subshell. Coming for D subshell, I will explain what is an exchange energy in this D subshell. If I take 3D4 and 3D5 subshells, I am taking 3D4 and 3D5 subshells. Here 3D4 means how many? This is dxy, dyz, dzx, dx square minus y square and dz square. This is also dxy, dyz, dzx, dx square minus y square and dz square. If it is having D subshell 4 electrons, then 1, 2, 3, 4. I can take 4 electrons. In this 3D5 how many electrons are there? 5 electrons are there. Among these two, which is having a symmetrical distribution of charge? You all should see first. Here in this it is half filled, so symmetrical distribution is more here. If it is having a symmetrical distribution, it is stable. You all know I have explained it previously that. If it is having half filled or completely filled means it is having a symmetrical distribution of charge. In this 3D5 there is a symmetrical distribution of charges taking place, but in 3D4 there is no symmetrical distribution of charges taking place because it is vacant here in dz square axis. Coming for the exchange energy. Exchange energy means here this electron exchanges its position with this electron in this subshell. How many? The number of exchanges is more means there is the releasing of energy taking place. More number of energy is released, and more number of energy is released means lesser the energy this orbital is having. So, this will be more stable. More the number of exchanges, more the stability. That you all should understand. Okay? More the number of exchanges, more the stability. If I take this 3D4, how many exchanges are there? This first electron 1, 2, 3. Number of exchanges is 3 for this. If I take here for second electron, number of exchanges is 1 and 2. Number of exchanges is 2. For third one, third electron, how many number of exchanges is possible here? 1 exchange is possible. Because these are all already exchanged. So, total number of exchanges is what? It is having total of 6. Total is 6 exchanges taking place in 3D4. There is total 6 exchange taking place. In this 3D5, how many exchanges are possible in first electron? 1, 2, 3, 4. 4 exchanges are possible for this. Here for second one, 1, 2, 3. 3 exchanges. Again for third one, 1, 2. 2 exchanges are possible. And for the fourth one, number of exchanges is 1. Total is how much? Total of exchanges is 10. They are having 10 number of exchanges in 3D5. Among this, as I said previously, exchange energy means here this electrons try to change its position with this electron. As the number of exchanges increases, what happens? The energy releasing of energy also increases. As the energy amount of energy released is more means what happens? Lesser the energy in this orbital. Lesser the energy means it is more stable. So, from this I came to know that 3D5 subshell is more stable compared to 3D4 subshell. I will take the example of chromium. I said that chromium is having a exceptional case, that is you all know the atomic number of chromium is 24. I can write this as 3d 5 4s 1. This is correct actually, but if I write argon 3d4 4s 2, this is according to Aufbau's principle. This is correct according to Aufbau's principle, but it is correct this method. This is the filling of chromium. Why I will explain. Why we prefer this is the best method for the filling of electrons in the chromium. Coming here, to calculate the number of exchanges, I will use some formula here how to calculate the number of exchanges in this. Here we will come to know how the filling takes place here. I will take the formula Mc2 and Nc2. Here M means was number of unpaired electrons in same direction, which are in same direction, that is taken as M. N is what? Number of unpaired electrons in different direction or opposite direction is taken as N here. First Mc2, I will take it for this chromium, I will explain first for this. Here Mc2 plus Nc2. Mc2 means M factorial by 2 into M minus 2 factorial. This is Mc2. Factorial means what? M factorial. Here M factorial, if it is having a 4 factorial means how you will calculate? 4 into 3 into 2 into 1. Like this we will calculate the factorial here. So coming for this, here in this chromium first, in d subshell, how many degenerate orbitals are there? 5. 1, 2, 3, 4, 5. Here I will take 5 degenerate orbitals, 1, 2, 3, 4, 5 and 4s here. This is 4s, this is 3d. How many d subshells are there? 1, 2, 3, 4. In S there are 2, that is in opposite spins. Here number of unpaired electrons in the same direction, how many are there? 1, 2, 3, 4, 5. 5 are there. So I can take 5 factorial by 2 into 5 minus 2 factorial. That is nothing but 5 into 4 into 3 factorial by 2 into 5 minus 2 is 3 factorial. 3 factorial get cancels. 5 4s are 20, 20 divided by 2 is what? 10. You will get 10. Here the energy is released 10E, I will represent it as 10E. And I will take the negative symbol minus 10E because the energy is released here and the process is exothermic in nature. It is releasing energy here, so it is exothermic in nature. Next coming for plus Nc2 here. In this 4s subshell, you all can see that there are 2 electrons, they are in opposite spin and the energy is required here for the 2 electrons to be in opposite spin. That energy is nothing but pairing energy. The amount of energy required by the electrons to pair is nothing but pairing energy. It is denoted by P, symbol P. Pairing energy means what? The amount of energy that is required to pair 2 electrons is nothing but pairing energy. So pairing energy is required here, that is P. Coming here for this, here D subshell 1, 2, 3, 4, 5, then S, 4s and 3D. How many electrons are there in D? 5, 1, 2, 3, 4, 5. In S, 1. All are in which spin? They are in same direction. The spin is in same direction. So how many possible? Mc2 is how many? Number of unpaired electrons in the same direction? They are having 6. That is 6 factorial by 2 into 6 minus 2 factorial. 6 minus 2 is 4, that is 6 into 5 into 4 factorial by 2 into 6 minus 2 is 4 factorial, 4 factorial get cancels, 6 5 is a 30, 30 divided by 2 is 15. Energy is also released here, and release means it is exothermic, so I will take negative symbol here, minus 15 E. Here the amount of energy is released plus, you all can see that previously I have told you all that the energy gap between this 4s and this subshell is not much more. There is no much more energy gap between this. So what happens in 3D subshell and 4s subshell? There are 2 electrons here, and in this 3D there are 4, 1, 2, 3, 4. 4 electrons are there. The amount of energy, that is, here what happens, the promotion of electrons takes place when 4s to 3D. There is promoting of electrons from 4s subshell to 3D D subshell. That is nothing but promotional energy. That is promotional energy, where we are going to promote the electrons here. We are going to promote the electrons because there is no much energy difference between this S and D subshell. So there is a promoting of electrons taking place from S to D subshell. So it is nothing but promotional energy, I will take it as delta E. Here when you see that delta E, this promotional energy and the pairing energy, the promotional energy and the pairing energy, they are almost nearly equal because both are requiring energy here. So they are nearly equal to pairing energy. Promotional energy is nearly equal to pairing energy. So what happens? It is equal to pairing energy. So this get cancels. When you see the amount of energy released in these two, which is more, having the more amount of releasing of energy taking place in this, that is 3D 5. There is more amount of energy is released, that is minus 15 E. More amount of energy is released here. So more the amount of energy released means what? More the lesser the energy of this subshells, and the energy it's having is less. So what happens? It is more stable. Therefore we say that completely filled as well as the half filled subshells are more stable. Understood, clear students? You all came to know about the exchange energy, pairing energy, and as well as the promotional energy. First you all should see whether there is a symmetrical distribution of charges taking place. More the number of symmetrical distribution of charges taking place, more is the stability. Okay? If it is half filled or completely filled also, you all should see that. And then in exchange energy, you all should see how many exchanges are taking place. More the number of exchanges between the electrons, more the energy that it releases. More the amount of energy that releases and lesser the energy in this orbitals. Therefore, it will be more stable according to exchange energy. And in this calculation, you all came to know that this is more stable compared to this. This is not stable. Okay, this is not stable, not less stable. This is less stable and this is more stable because it is having half filled electronic configuration in a D subshell. So it is clear, I think so, for you all students. In this session I have explained you all completely about the filling of electrons, that is according to Pauli's exclusion principle, Hund's rule, Aufbau's principle and N plus L rule, as well as I have explained the exceptional cases of the filling of electrons of the 30 electronic configuration, atomic number having 30 electronic configurations, and in that you all came to know that copper and chromium having a exceptional cases, and that is explained in why the half filled and completely filled subshells or degenerate orbitals are having stability more. In that I have explained you all the concept of symmetrical distribution of charges as well as the exchange energy, promotional energy and also the pairing energy. In this session completely I have explained you all about the atomic structure. First unit has been completed. You all came to know about in the first unit about the Bose postulate, his 4 important postulates you all came to know about the 4 important postulates as well as the limitations of Bose atomic model and also the de Broglie's dual nature of matter and radiations as well as de Broglie's equation and Heisenberg's uncertainty principle as well as the hydrogen atomic spectra. You all studied about the hydrogen atomic spectra and the Schrodinger wave equation for an electron in 3D space as well as psi psi square. You all came to know about the psi psi square. Also the hydrogen Schrodinger equation for hydrogen atom. I have explained the Schrodinger equation for hydrogen atom as well as the hydrogenic and radial wave functions for the hydrogen atom. I have explained that also for you all as well as nodes, radial and angular nodes, quantum numbers and also the orbital shapes of different orbitals, and in this session I have explained completely about the filling of electrons and electronic configuration. So, it is clear now for you all about the atomic structure. Thank you, students.